Friends, for centuries, humanity has gazed at the stars, dreaming of the journey beyond our terrestrial home. We have sent probes to farthest reaches of our solar system, landed rovers on Mars, and even dared to touch the sun. But these journeys, while monumental, are just the beginning. The cosmos beckons, vast and enigmatic, promising discoveries that could redefine our understanding of the life itself. Yet, there is a fundamental challenge that limits our reach. The distance. It's quite large in space. We know that. Even our closest planetary neighbor, namely Mars, can take months to reach. The gas giant years, and the stars thousands of years, thousands of centuries sometimes, with current technology. What if there was a way to break free from this cosmic speed limit, to shrink the vastness of space and propel us further, faster than ever before? This isn't science fiction, this is the promise of the nuclear power, unlocking the new era of deep space exploration. So, what is holding us back? Primarily, it is the limitation of the traditional chemical propulsion. Rocket engines, whether they burn liquid hydrogen and oxygen or other propellant, are incredibly powerful for lifting off the Earth, but for long duration mission in space, they become incredibly inefficient. Chemical rockets operate on the principle of expelling hot gases at high speed. The more propellant you carry or burn, the more thrust you generate, but you also add significant mass, which requires even more propellant to accelerate. It is a diminishing returns problem. This tyranny of the rocket equation means that reaching destinations like Jupiter or Saturn, let alone the interstellar medium, requires years of travel. This extended travel time means more resources for life support, increased risk of equipment failure, and longer exposure to cosmic radiation for human crew. We need a paradigm shift. We need a way to generate immense power and thrust with minimum fuel. And the answer ironically lies in the same force that powers the sun, which is the nuclear energy. Nuclear propulsion isn't about detonating a bomb in space, it's about harnessing the controlled power of nuclear fission. In essence, it's about using a small efficient nuclear reactor as the heat source for rocket engine. When the heavy atomic nuclei like uranium 235 are split, they release an enormous amount of energy in the form of heat. This heat is crucial ingredient. There are two primary types of nuclear propulsion we are focusing on for the deep space journey. Number one is the nuclear thermal propulsion, or in short, also known as NTP, and nuclear electric propulsion, also known as NEP. Let us start with nuclear thermal propulsion, which is in short NTP. Imagine a standard chemical rocket, but instead of burning fuel, you are superheating a propellant like liquid hydrogen using a nuclear reactor. Liquid hydrogen is pumped through core of the compact nuclear reactor. The reactor heats the hydrogen to incredibly high temperature, thousands of degrees Celsius. This superheated gas then expands and shoots out of a nozzle, just like in a chemical rocket, generating thrust. The key advantage here is the specific impulse. This is a measure of how efficiently a rocket uses its propellant. NTP engines can achieve specific impulses 2 to 4 times higher than the best chemical rocket. This means for the same amount of thrust, you need far less propellant, or you can go much faster with the same amount. Now let's look at the nuclear electric propulsion, also known as NEP. This approach is a bit different. Instead of directly hitting the propellant, nuclear reactor generates electricity. This electricity then powers advanced electric propulsion system like ion thrusters. Ion thrusters work by ionizing propellant, typically a xenon gas, and then accelerating these charged ions using electric fields to extremely high velocity. The exhaust velocity of an ion thruster can be 10 to 20 times higher than a chemical rocket. While ion thrusters produce very low thrust, think of it like gently pushing a bowling ball. Then they can operate continuously for months or even years. Over time, this constant gentle acceleration builds up incredible speed, far exceeding what a chemical rocket could achieve. The trade-off is the acceleration. You won't get to orbit quickly with NEP system, but once in space, where there are no atmospheric drag, an NEP-powered spacecraft can reach truly astonishing velocities, making long-duration missions to the outer planets and beyond significantly faster and much, much more efficient. The benefit of nuclear propulsion are profound and multifaceted. Firstly, the speed. A journey to Mars, which currently takes 6 to 9 months, could be reduced to a little as 3 to 4 months with NTP. This dramatically cut down the mission duration, reducing the time astronauts are exposed to the harsh radiation environment of space and requiring fewer life support resources. For mission to outer solar system, the benefits are even more striking. Imagine a probe reaching Jupiter in a year instead of 5, or Saturn in 2 instead of 7. This means, this opens up entirely new window for scientific discovery, allowing us to study dynamic processes on these gas giants and their moons over a shorter timelines. Secondly, the payload capacity. Because the nuclear engines are much, much more efficient with their fuel, they can carry less propellant mass. This mass budget can then be relocated to more scientific instruments, larger habitats for astronauts, or more abundant systems for increased mission reliability. Thirdly, the mission flexibility with greater power available. Nuclear powered spacecraft could perform more complex maneuvers, orbit distant planets, or even carry robotic landers and return samples with greater ease. They could also power robust communication systems and onboard scientific experiments for longer duration. And perhaps most excitingly, nuclear propulsion takes one step closer to interstellar travel. While still a distant dream, the efficiency gained from nuclear power lay the groundwork for concept that could one day take us to other star systems. The idea of nuclear propulsion isn't new. In the decade of 1950s and 60s, during the heights of the space race, ambitious programs like Project Orion explored using nuclear bombs for propulsion. While fascinating, this approach was later deemed impractical and environmentally problematic. However, the same era saw the development of Project Rover, uh, also known as NERVA, nuclear engine for rocket vehicle application. These programs successfully demonstrated the feasibility of the nuclear thermal rocket engines, conducting numerous ground tests in Nevada desert. These engines were incredibly powerful and efficient for their time. With the advent of the space shuttle and the focus on Earth orbit, nuclear propulsion research dwindled for a time, but as humanity set its sight on Mars and beyond, once more nuclear power is making a significant comeback. Today, NASA is in partnership with Department of Energy and private industry is actively developing a new nuclear propulsion technology. Programs like Kilo Power Reactor using Stirling technology, also known as CRISTI, has demonstrated compact, robust fission reactors suitable for space. More recently, DARPA demonstrated rocket for agile cislunar operation, also known as DRACO program, aims to build and fly a nuclear thermal rockets in space by 2027. This would be a monumental step, proving their technology's readiness for operational missions. The renowned focus on the nuclear propulsion is a clear sign that the scientific and engineering communities recognize its critical role in expanding humanity's footprint in the solar system. While the advantages are clear, developing and deploying nuclear propulsion isn't without its challenges. Safety is paramount. Designing reactors that are safe to launch from Earth, operate in space, and pose no risk in the event of a malfunction is a primary concern. Modern designs incorporate passive safety features and robust shielding. The reactors would only be activated once safely in space, well beyond the Earth's atmosphere. Cost is another factor. Developing these cutting edge systems requires significant investment, though long term benefits in terms of mission capability could outweigh the initial expenditure. Public perception and the policy also plays a crucial role. Educating public about the controlled nature of space-based nuclear power, distinct from nuclear weapons, is essential for gaining support. Despite these hurdles, the momentum is building. We are seeing international collaborations, increased funding, and dedicated teams of engineers and scientists pushing the boundaries of what is possible and what is not. The path forward involves continued ground testing, development of new materials capable of withstanding extreme temperatures and radiation, and eventually in space demonstration to prove the reliability and performance of these revolutionary engines. Imagine a future where journey to Mars is a routine commute, not a monumental expedition, where permanent human outposts thrive on the red planet, supported by faster, more efficient supply lines. Imagine dedicated missions to the oceans of outer solar systems like Europa, Titan, and Enceladus, where robotic submersibles powered by compact nuclear reactors could dive into alien oceans searching for signs of life. Nuclear propulsion isn't just about faster travel, it's about enabling a sustained human presence beyond Earth. It's about unlocking truly ambitious scientific endeavors, allowing us to explore the cosmos in a way we can only dream of today. It's about transforming humanity from a planetary species into a truly space-faring civilization. The journey beyond Mars will be challenging, but the power of nuclear propulsion, with this power, we are poised to take the next giant leap. It is a leap that promises to redefine our place in the universe, inspiring new generations to look up and wonder not just at the stars, but at the incredible future we are building among for them. So, friends, thank you for watching, and don't forget to like and subscribe, share, subscribe for more content of the cutting edge space exploration. Thank you, and I will see you again in the next one.